record this one. Am I recording? Yeah, I think I'm recording right now. Okay, let's go ahead and before come to the, I think before we're gonna get into this one, we can have a look at it. Even the this one, midterm test. Do we have a midterm test? Yeah, this one. It's only MCQ. I think that you have to. Most of the questions are multiple choice questions, but so what do you think that, see, number one, we have only 10 questions on this one. We can just finish this one. What is the difference between principal component analysis and the principal factor analysis?
Principal component analysis is a type of factor analysis.
Can be rotated or no difference, or PC must be the minimum eigenvalues or criterion to select that one, or communalities is one. In fact analysis, different community estimate used. In fact analysis, factors can be rotated. PC does not allow rotation. In both cases rotation can be done, we know that. There's nothing there, no difference. There is a difference. PCA must use the minimum eigenvalue of one criterion to select the number of factors. Minimum? No, there's no such thing. So then when you go that narrow down, it seems like you're gonna we are left over with this one, no? We are left over with this one. See? So is that true? This one you saw this one at a certain point. Can you remember? Look at this one, communalities. Let's go back to. Here, okay. Here, see. When loadings are using, see. Here you get 1, and this is also 1. These are why I'm talking about the community. See, added to 1. Let's look at another way to have a look at it. This one. Can you remember we did this one? Look at this way. Now, when the eigenvectors are used, when the eigenvectors are used, still you see, then if I'm using eigenvectors, it looks like this. If I'm using load-in, see, like this for this particular example, see, they've added to 1. See. Here I'm using the load-ins. When you use the load-ins, load-in should be that eigenvalue, square root of the eigenvalue times the eigenvector. You can remember that we had that discussion. But when you see, when you sum up squared of these load-ins for that x, that means the communalities, you get 1 over here. But even whether you are using load-ins or eigenvectors, here I'm using eigenvectors. Let's see, this is on page. This over there. So here, no? See. 1, 2, but we can set up in such a way that we get, see, sometimes we get eigenvalues here, sometimes we don't get. See? So in both places. So that way that the PCA, the community estimate is 1. In fact analysis, different community estimate is that one, the one that I showed you, that one was the PCA. Can you remember? That was PCA. Okay. So from the PCA, we got those values. Okay. So the way that I have written that one. Okay. So So the answer should be B. Look at this one. Part 2. What do you think? I conducted a principal component analysis of 6 economic measures. Principal component. Loadings on the first factor. Actually, it's the factor means it's a factor analysis actually. Given below, how many of these measures would you consider to load substantially enough on the first factor to be considered in the interpreting the factor? If you really want to consider this factor to be like a reasonable factor, that what do you think, how many of these measures would you consider to load substantially? How many of these variables would load on this factor? How many of them? See, you see the loadings. By looking at the loadings, you can figure out if anything is, if any loading is more than 0.6, around
Yeah.
0.6, yeah, then we can consider them to be that reasonably that load into that factor. In that way, you can use that particular factor to that consider. You can consider that factor. See, so this pretty much every variable, like see, at a little rate percentage or around more than 0.6, 0.6, 0.6, 0.6. See?
If we had a second or a third one, they would have to be less, right?
Yeah, yeah.
Yeah.
It is like a criterion. Like some people go with the 0.5, some people go with the 0.6. Okay. So if it is like all the loadings are more than 0.6, around 0.5, then that would be that they are loading for that to contributing to that particular factor.
Mhm.
So in that way, we can say what? Substantially,
All of them.
all of them, all
Mhm.
of these load substantially on factor 1. All
Even
the,
if one of them is negative, that wouldn't matter.
yeah, that, it doesn't matter. You can take that absolute of that one. I mean,
Okay.
like, negatively that one, okay, but it's negative in the negative side and positive side. We can say negative 0.6 to positive 0.6. Okay. So this one, see, we can consider this one because you can consider that just the magnitude.
And it just loads, but it's in an opposite direction.
Opposite direction, yeah. That's in opposite direction. Plus that you can consider just the magnitude. Okay. And that pretty much all load substantially on factor 1. I conducted principal component analysis of 6 economic measures. Given the results on the following page, how many factors would you retain and why? It's a piece of cake, you know that. Eigenvalues, difference, proportion, cumulative, you don't have to look into that one. So many. How many factors you're going to retain? There are so many criteria we can utilize, but the most famous one would be Kaiser's rule, no?
Mhm.
Based on the
Only
eigenvalue, the Kaiser's rule, you'd only take number 1.
Number 1,
Mhm.
only one factor, retain one factor only. That's it. Basically, you can simply say that one, or that by looking at the street plot, see, yeah, it's gonna flatten out, see, but there's no see, place where it's gonna be flat off. So, but see, all go like this, but this will be the best way to have a look at it. More than one, lambda is more than one, eigenvalue is more than one. In that way, you're gonna retain only one factor. That means principal component, only one principal component is enough for you to do the whole that analysis at the end of the day. Okay, that's one. Okay, let's keep going. Rewrite the analysis below to require squared multiple correlation as a community estimate. Verimax rotation. Anybody? How do you write? If you use the Verimax rotation, that same thing, just a rotation, same thing, the factor, data, you have a factor, you have a data, okay. Then you have to add what? Rotate only. Can you remember? Rotate. See? Require to squared multiple, see below to require, see? Squared multiple corrections, correlation, see? Rewrite the analysis below to require squared multiple correlation, squared multiple correlation. See? As the community estimate and a Verimax rotation. See? So you can write which way? You can write The variables. Just one thing. Rewrite the analysis below to require square. Community estimate and the variance rotation. Okay, these two squared SMC. Okay, priors, you're gonna put the SMC, rotate, you're gonna put the, you can say the priors, you can look for the priors. Okay, I'm gonna write here for you to see. Crop factor and the data. What's the name of the data? What's the name of the
It just says my data dot example.
my data? Okay. Sample. Okay. Then you can go to the priors. Priors should be, they are looking for multiple. You're looking for squared multiple correlation. Squared multiple correlation. Squared multiple correlation. And I'm gonna write, okay. You can see that. Squared multiple correlation and rotate. Rotate. Variance max, very max. You include that. Those are the trials. Squared multiple correlation and rotate. Very max, and you put the data, and this is a procedure. Okay, see, number 5, you have completed a principal component analysis of a set of data. The eigenvalues for the first 5 factors are 2.789, 1.1.23, 1.021, 0.978, 8.836. And using the output below from the parallel analysis program by O'Connor with percentile 0.95, how many factors would you retain according to that criteria? Principal analysis criteria. How many? Can you remember we had that discussion?
Are we going back to, are we looking at the table from, hold on, what? Oh, the data's up here. Sorry, I couldn't.
That's okay. You see that one, no? You see that, no? Do you see this one?
Yeah, we would retain 2.
Okay, retain 2 because you're gonna compare this one with this guy. No, if it is more than that, no. Am I right? Can you remember? Yeah. This with that, this with that, that with that, this with that, that with that. 5 coming from your original eigenvalues will be compared and contrasted from those coming from the Monte Carlo simulation process based on this parallel analysis. Can you remember? So this one is 2.78, 2.789 more than this one. So you keep 1.123 more than 0.050. 1.021 is less than 0.036. 970 less. So these two, no. You're gonna keep how many? Then how many factors you are planning to keep at the end of the day? How many factors? Okay, we're not gonna drop the original factor variables. Okay, you know that this discussion. Okay, we do not drop original variables. We are writing some new variable as a linear combination of the old variables. Now we have a question: how many components should be linear combination should be retained or created? That has been done through certain criteria. This is one of them. You can compare and contrast the eigenvalues coming from original data with those from the Monte Carlo simulation based on the vector parallel analysis. So you're going to keep 2 factors. Okay, 2 factors. Okay, principal component component of factors. Okay, that's the idea.
Professor, why are those values so close to each other? Like those mean values and the percentile values, why are they so close to each other?
That's the way that I think they have been given like that. No, this is not, see, they have given for.
Is that always the case is what I'm saying?
No, that's not the case. I mean, like they have given for us to that, they have given this one. This is not coming from anything. They just, see, they say, okay, see, it's not based on any data set or anything like that. No, you see, it's the way that how they came out. Okay. So, but anyhow, what we are trying to do, regardless of that they've been close to each other, what we're gonna do, we're gonna contrast these two. This one is second one, this one is the third one, this one is the fourth one, this one is the fifth one, done. Because they haven't given more than that variables, okay? But
I was asking because that was the case also with like our example in the homework. The means were like 1.02 and then the percentile is 1.03. So they were like those
close to each
values.
other. Okay.
Yeah.
But the ones that are shown in percentile, those are generated just by chance. They're randomly generated, right?
Mhm.
But when
Yeah,
you use,
they-
of course, when you use a seed, you'll get the same thing over and over. But what we're saying is that the ones we've generated through our data that are greater than what would be generated strictly by chance is what we retain.
Yeah, that's right. Yeah, but this one, she was concerned by these those were so close to each other. That's, yeah, but in this case, but even in the way that we had done based on that, how many simulations you have done, the more simulation you're gonna do, sometimes they're gonna be sparse out, you see. See? But how many simulation did you do for your that homework?
I
did 100.
Oh yeah, you have to increase that 100 like a 1,000 millions, because be careful, your computer gonna get stuck. But what I'm trying to say, yeah, that when you do like a large number, sometimes they're gonna be just spread out. But doesn't matter that, see, they were just they were centered around a certain place, because there should be a reason for that one. See, look at these values, even that they close to each other. So they were centering around the same area, see, same places, see, around the same value, see. So for the when you run that homework one, so can you remember the homework? What are the eigenvalues you had? The original eigenvalues. Do you have that eigenvalues? What are the eigenvalues you had for
on our
original?
homework.
In a homework, yeah.
Would it change depending on which variables we chose? You know how like we all chose
No.
different
I'm talking about that. These numbers. You should get this one. Everybody should have the same thing for this one. Pretty much, yeah. Based on that, how many variable principal component they are planning to keep it. Other than that, their values. I'm talking about the values. See? Eigenvalues. Originally, that we got the eigenvalues. Can you remember? We had a data set. No, we had a data set. From the data set, we can get that eigenvalues. So the data set, from the data, you can create the covariance matrix. Variance matrix. Covariance matrix will be split into two parts: eigenvalues and the eigenvectors. One for the value, one for the direction. So those values, and then later on when you are using that parallel analysis, are they like close to each other? That I will look at it. Can you remember that one? Back to this one. Okay, this one cannot work. Means fact analysis. Okay, let's run this one. With this one, no fact analysis. 5.3, 5, 1, 1, 1, 1, 1, see. See, they were not that much, see, differ from each other, see, except for the first one, no? Except for the first one, they were centered pretty much at the same place. But when we had like a different example that I did in the class, we had drastically two different numbers. Can you remember 1 and 3? Yeah, 1 and 3. No, can you remember 1 and 3 like that? But here, see, like that one. But when you're gonna run, let's see, it's parallel and it's so data set. Okay, I put. Let me run this one and see. I put only see, see. They were kind of like a generated the same like in a that see, around the same kind of like a value, see, centered around a certain value, see, not too, see, not that much of a variability, see. But the because that this one already embedded that Kaiser rule inside, I think that's why that always go with the one, close to one, see, you know, it's gonna be around that one. They see Kaiser rule, we're gonna say that they're gonna set that criterion as like a Kaiser rule. Anything above that one, we can easily get as a, like a, considered like one of the principal components. See, look at this, all the values, see, centered around one. That was the reason. Yeah, even over here we had the same situation. So that's the same thing that they pretty much see. So it's gonna be kind of like in that way that Kaiser rule being already embedded within this system. So anything that beyond that one easily you can figure up. You see, it seems like the same thing that we were talking about over here. These two, see? Let's say these eigenvalues, see, that except for this one, like roughly that this is more than one, but let's say that this one, these two mainly. See? If it is one, we don't even consider. If you're going to round this to like a one, the one decimal place, see, these are the two that you can get it selected based on the Kaiser rule as well. No, see, based on the Kaiser rule, you're going to select these two. I'm talking about that. If you're going to round this to like a first decimal place, but more or less that we can get like that same number, or sometimes not the same number, but we're gonna get the approximately the same number of that principal component based on that pretty much all the techniques, because they're not gonna have any drastic changes. If the drastic changes, that method has not been accepted by the statistical arena, because the statistician, the one method, but this is a different kind of method. This method is far more powerful. We discussed the other day, because rather than stick to one eigenvalue, you're going to get a whole bunch of eigenvalues, and because of the randomness, and then you build up its mean value or whatever the statistics you are interested in. They are interested in the percentile. In the beginning, they were interested in the average. Based on the average, we can get this done too. That's the criteria. See, here they were using percentile, 95 percentile. Then you can go to the quartiles, based on quartile, third quartile, 75th percentile, something like that. Whatever the statistics that, they were stick to this 0.95, and that way that to come up with like a fair that results at the end of the day, or sometimes inconsistent with that results from the Kaiser rule. Okay. So they are always like this. Okay, then let's go to the next one. You are interested in assessing whether same store sales are improved this Christmas season compared to the last year. So you're going to take into account the time period, trend, okay, certain trend. Okay, you have November sales figures for 230 stores measured in both 2014 and 2013. You're going to compare 2 years, 2013 and which of these analysis would be appropriate? Select all that apply. One-way ANOVA, two-way ANOVA, paired t-test, independent sample t-test, repeated measures ANOVA. What do you think? This like a no, before, after like that. You can say before, after that year, the next year. You're going to compare two. You have only two groups only. This is the
So-
final.
One way ANOVA would be okay, right?
One-way ANOVA. When we gonna utilize the one-way ANOVA, we have a categorical variables or the groups. Can you remember their average will be compared and contrast.
Their averages.
Averages, no? Can you remember? But here they say, hey, I'm trying to improve this one based on that last year and this year. They're gonna compare 2013 and 14. Before, after. You have something before, after.
Would it be
Repeated
the
measures.
pair
Sure.
t-test?
Paired t-test, yeah, one of them paired t-test.
And the repeated measures ANOVA.
Repeated measure
Yeah.
ANOVA. That's the beginning of the repeated measure ANOVA beginning. That's the beginning. Okay. So that means this one that see. So they have, that's the very beginning. See, can you remember we were talking about the single? Before that. See, this is before. This is before. This is after. Okay. So before means in 2013. This is 2014. Then oh, I ran out of my ink. I had to put a new.
Is it because we're interested in the differences and the difference between one year to another?
Exactly, and before and that then we can say before and after, no? Before and after. See? So they have how many? Oops, no. So they have how many? 230 stores, see? Actually, 230, okay. So that means, see, this is the store, second store, blah, 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 230 store. See? Then you have the reading, see? You can read it. See? Then you can get the what? You can get the difference, no? Can you remember? You can get the difference. That's the same difference that we were talking about that at a certain point the other day that when we were going through. No. See the difference between any two of that one. See this part only. Think about this part. See, I took the y1 minus y2. That difference. Paired t-test. This is called the paired t-test actually. See, this is the paired t-test. So you do the same thing for that one too. What kind of a distribution you are utilizing in order to run that one. This data, whatever the data being repeated, if you repeatedly do this one again and again and again, that difference is gonna divided by their standard deviation divided by the square root and number of that stores or number of individuals, number of subjects, that will be distributed according to a t distribution with the degrees of freedom n minus 1. So this one is called the paired t-test actually. This is the paired t-test. Or paired, this will be utilized in order to check whether there's any improvement in that this sales than in 2014 than in 2013. That's the same thing. See? So So if I write this one here and then show you, okay, I'm gonna write first. D would be D bar difference. See? Standard deviation of this one divided by square root n, which is distributed according to n minus 1. D bar means that, see, D bar here means, see, before and after. See, D means Y. Y means, let's say Y equals sales. Y before, sorry, after, Y before. So you get the differences and then you can find its average. D bar. Should be, see, summation of this YA minus YB, see, divided by 230. Those differences. And then we're gonna, you know how to find the standard deviation for that one, standard deviation. For that difference, standard deviation, see, that different standard deviation. Not this one. Here we have to go to that one, but standard deviation, they already calculated here. You know how to calculate that one. You get the reading minus its mean and square, and then keep, if you keep going that one and divide by n minus 1 if you need. Okay. SD would be 1 over n minus 1 square root summation any d minus d bar squared. You go to the each reading, okay? Each reading has a d. If you want, you can put the di, but I don't want to put too many. Okay? You go to the difference and subtract the mean, the total grand mean, okay? And then sum them up, and then get the sum them up and divide by n minus 1 and take the square root on that one, will give you this one. Okay? So this is called the paired t-test. That has been paired t-test. This is dependency, dependent test. If you have an independent test, can we use independent test for this kind of scenario? No, before and after. Independently, you can check between two groups. That's where the ANOVA is heading towards. That's the very beginning of ANOVA. This is the very beginning.
We only use it if the groups are independent of each other, but right? That's
plus more than two groups. Plus more than two.
More than two groups, yeah.
Okay, that's the beginning of analysis of variance. This is the beginning of repeated measures analysis of variance. That's the regular analysis of variance beginning. So this is the beginning of, see, this is the beginning of, I'm gonna, I write here, this is the beginning of repeated measures design, see, RMD. RMD start from here. Can you remember this model is nothing but equals to single group repeated measures, see? Single group repeated measures design in another way, or paired t-test, dependent test. See, that's the beginning of RMD or single group RMD. And if you consider this one independently, see, let's talk about different one that independent two groups, okay? See, you have a different example, okay? This one, group one. Group 2 or population 1, population 2, and you have, say, some different kind of experiment, but I'm going to use the same now. See? Then you're going to you say that this Y would be sales, how sales going to be for a certain group between a male and female or something like that kind of a comparison within the two countries, how the sales been done. And the two stores, you're going to compare, contrast like that for a given year, something like that. Then you're going to do what? What is you're going to use? You can use the T, but this time you're going to use what? Y1 minus Y2. This one I'm going to call Y1. This one Y2. Okay. y2 bar divided by this one standard deviation of y bar by this one divided by no, that's it. Right like that. Okay. The standard deviation of that one will be distributed according to df. See? But based on different scenarios, they're going to change to, okay, I'm not going to get in there now, okay, because the analysis variance you guys have already done. But this is the beginning of, this is the beginning of, this is the beginning of ANOVA, regular ANOVA, regular or standard. Another way, this one I can say this is the beginning of RMD measure ANOVA. The other one. So by looking at this one, you can figure out it's going to fit in into the pair t-test as well as the repeated measures. So yeah, t-test. Okay, let's go to the next one. Given the results below, answer the following question. What percentage of variation or variance in the dependent variable insecure has been explained by this model? How much variance has been explained by this model? This is what kind of model is this? R squared, coefficient of variation, root mean squared, error, insecure mean. Insecure means that's a y. Okay? It's the model, it's the error, it's the total, degrees of freedom, sum of square, mean square, F value, probability, GLM procedure. See? This is look like a what? Regression or analysis of variance? No. Either way, that even regression and analysis variance are the counterparts. Okay, they are like a twins. They go to travel together, and then one can explain by the other, and vice versa. So this here, how much variation has been explained by looking at which matrix or which statistics you're going to figure out how much variation has been explained. You see, they brought this one, you know, this one, how much they say this sum of square total is nothing but the sum of square total error. This is the error of what? Null model. Can you remember we had that broader discussion in previous classes? Null model. In the empty model, this is the sum of squared error. You're going to bring this much of to the, you have this much of that sum of square. 1025 right around. Okay, from that one, by introducing a certain model, you have reduced that one this much. Only this much has been explained. 145 1. The rest leftover again. This is the leftover sum of squared error from the empty model. This is, you might gonna say this is a two-group model or regression model. Doesn't matter. There are three types of models we talk about previous class. So this again is when this much, see, this much being explained while you have this one. That's the ratio. 141.947786 divided by 1025.958384 is the that how much being explained. Okay, we have a name for that one, two names for that one. Can you remember those two names? Anybody? Proportional reduction in error, pre. Can you remember pre? Proportional reduction. I'm gonna write this down here and then I'll show you. Okay. Sum of squared model. Sum of squared model is 141.9. Okay, for my termin 95. Okay, and sum of squared total, I would say 1025.96. Okay, right, these two. Okay, then see, if you divide this by 141, 13.95 divided by 1025.
13.83.
13.83. You see that one somewhere in that printout. See, you see that one somewhere. Where do you see that one? R squared. See, that's nothing but R squared. That is nothing but R squared. Okay, I'm gonna come back to this one, and this one called SS model divided this sum of squares model. This one sum of total. Oh, error. Sum of squares from the empty model. Same thing. That's the same thing. See? So it's gonna be like around 13 point something, no? 13. I'm gonna put this number. Okay. Let's say 13.83 and times 100%. Okay, 13.883, 84.84%, because I have multiplied this by 100%. See, this has a name, sum of squared. This one divided by sum of squared total. This one has a name. It's called R squared, or we call this one PRE, proportional reduction in error, or R squared. You can simply go to the R squared and have a look. Okay. Sum of squared model. On the other hand, see, if you will believe later on, we can adjust that one. We're going to adjust by taking, instead of this one, we're going to take their degrees of their relevant degrees of freedom to adjust that one, because even if that you have introduced that when you're going to go to the multivariate regression, even if some independent variables not going to vary importantly, significantly contribute to that explanation, explaining that dependent variable, it seems like a very moment that you're going to add, the more you add the value, the higher the value of R squared. That means like you will be misled. You are misled and say, yo, R squared is a very high. In that way, this is a good model. This is a good fit. My data are very good fit for this given model. No, that's like a kind of like a misleading, because there's some part been unmasked that has to be unmasked. That's why we're going to get into the R squared adjusted later on. Okay, because some multicollinearity and all kind of stuff being involved with that one. I think we talk about that one in broad range in previous classes. Okay, so anyhow, let's go to, so that should be what percentage is nothing but 13.84. Would you reject the null hypothesis of no difference between the means? See, no difference between the means. That means they are trying to say the null hypothesis would be what? No difference between the means.
Yes.
Yes, no? Yes
Yes.
or no? Yeah, I think yes, no?
Yes. Mhm.
Because by looking at what? Looking at the, simply looking at what? Simply looking at the p-value. P-value. P-value is approximately 0 or less than 0.05. Okay. Since this is, see, yes. Null hypothesis means there's no difference between the means. All the means the same. And versus its counterpart would be what? At least two means are not the same. Okay. You know how to write that, this one. Would you reject the null hypothesis of the no difference between means versus its counterpart? At least two of them, two means are not different. Okay. Okay. You see, You want to know whether the new marketing campaign has increased sales. There are 29 stores that use the new social media marketing strategy and 201 that did not. You write the following program. Which of the following mistake did you make? Select all that apply. If you have a that something like that, this would fit in into what kind of a that this definitely repeated measures for this is for sure this belongs to repeated measures design, R&D, or repeated measures analysis. But I want to know, even with that one too, it belongs to what kind of, there are several categories we talk about. One in between, and how many between, how many within, like that. If you want to have a look at it, that should be like it fitting into what kind of a setting, like at the end of the day. Can you remember that to make it easier? This is what I'm talking about here. So, no, sorry. Oh, not this one. No, it should be in our notes, I think. If I'm right. Let's see. No. Yeah. We have a several types. Single group, see, repeated measure design. Then we talk about that one-way repeated measure when time is the within subject, something like this. Or one between and one within is the between variable. This is a between variable. This is a within variable. One variable. One between and two within. And two between and one within. Two within and two between. So in that categories, this particular example gonna fit in where? So on the other hand, if I go here, this one repeated measure, see. So single, see, multivariate match pairs. Okay, see, one between, one within. This one single group repeated measures. Okay. Or see, one between, one within. First one, just a single group R&D, repeated measures design. Second one, repeated measures that but repeated one group, but still that is going to happen over time. Okay, over time. The second one. And the third one between and one within repeated measures, something like that. See, you have a diet, the programs. There are 3 diet programs over here, including even the control one, and that they are, see, the y values for that several groups. Okay, that one. And then we have one between, two within, then two between, one within. Okay, like that. So this kind of fitting into which one? This result I'm talking about. You know definitely where the mistake is, because it's not a big deal. Mistake is where? Where's the mistake? What is the mistake here?
Would it
Proc
be
Nova.
line 1? Because you
Line.
don't do Proc Nova, you do Proc GLM.
Exactly, that's it. And then yeah, that's it. Okay, that's the answer for that one. But I'm going beyond that one, and I really want to know, go back to that one and see this fitting into that what type of look like. See, you have a market, 2 levels, no? Market, 2 levels. Here sales 1, then model. See, this is the class. See, looks like it's one within, one between. Is that right? One within, one between. But see, you have a repeated, you have the repeated variable. Repeated variable has a name. It's a within variable, no? Within variable. For a given any individual or any person, that this will be the, that, see, this is the within one. Then what is this one? This is between. It's the between variable. It's the between variable. is the within variable. It has a two levels. So
So it's marketing strategy versus no marketing strategy, right? Marketing strategy
exactly. What the
versus the
control
control
group.
group. Mhm.
Exactly. Yeah, that's yeah. Like so. See, then we can talk about this one. See, again here we have so the market. See, type of market. This one within variable, and it has a two types. No, can you remember market one and market two? Correct. Market one and market two. See, two levels, no, two levels, 1 and 2, and it has a between group is this one. See, so this one class, or you can say between group, between y is nothing but you can say campaign. I'm gonna write here campaign. So you're gonna have a marketing campaign. Versus control, you don't do anything. See? Then here you have y equals what? Sales. Then if that's the case, at the end of the day, you have a here sales 1 and sales 2. So this gonna one within and one between repeated measures design. That belongs to that. We don't ask that one, but we built up more knowledge based on that one. Market 1, market 2. Based on that one, you have a sales 1 and sales 2. Sales 1, sales 2 equal to the campaign. They call the campaign for the class. Okay. Okay, this one. The following output was obtained from an evaluation of an intervention designed to raise student ACT scores. Students were randomly assigned to one of two conditions: online practice test or classroom preparation. Was the experiment successful in raising test scores? Refer to the table above to justify your answer. What do you think? This again belongs to what? If you see this kind of a one, this kind of a that table, okay, let's go back to the previous question and then something similar to that one. Let's look for in our SAS one within. Okay, see this example, one between. Sorry, okay, one between, one within repeated measure. See, you have the see. These are they are built in up the data. See, this one variables. Okay. So this is the class. This is the between variable. These are the between variable. So the time would be your what? Within variable. Let's run this one and see what it has in the Nova table. See, look at here. The GLM procedure, univariate procedure. What do you have? See, you have a time, then you have a interaction term. And again, within one being the array would be the within one. See? So it looks like this. So that means that by looking at this one, you can figure out this fitting into something like that. See, one within one. So see, test score is same like a time. So the test score would be your within. Condition between here, that would be between. Then at the same time, they're going to build up even the interaction term. See, interaction term. Look at the interaction term. Would that be significant or not? P value. Look at this one. Would that be-
Not at the 0.05.
No, not at the 0.05. Exactly. See? So this gonna be significant. So the see. So how you gonna that the same way that we did earlier? If you're gonna draw this one, sorry, I'm gonna setting into this one. See? Again, then we can say that I would say within variable would be what? Sometimes they call the repeated variable. Repeated one would be
Test.
test score. Exactly. ACT test score. ACT test score, or they simply call the test score. And then you have, see, how many levels you have? ACT, previous or old one, old method, or ACT, see, new results. New results. See? And then your control or between var or class would be nothing but condition. Condition. What's the condition? There are two conditions there. Online practice test or classroom preparation. Classroom preparation. These are levels. These are the variables. See? This is a variable, this is a variable. And this one. See? So the test scores. Okay. So the y would be test scores. But anyhow, related to that one, we're gonna ask whether that this gonna be significant or not. See, we can say that the interaction term not significant. See? And then this one would be significant. See, more than less than 0.05. See? So there's an improvement. See, revision. See? Student were randomly assigned one of two conditions, this one, and then was expected to raise in their test scores. Yes, but they were trying to in two ways. Okay, test scores. See? But this condition part has been taken out. See, but condition with the test score, they go both as an interaction. Condition means like in both methods. See, that one's been taken out at the level of 6.05. Okay. You have conducted repeated measures ANOVA with the following design. You are trying to brew the perfect coffee. You have 100 tasters. Each test 4 brands, label A, B, C, and D. Rate them on a 0 to 100 scale of coffee perfection. Since you are the producer of the coffee brand A, you are only interested in comparing it with the other 3 brands only. Write the SAS code to produce this result. This is what? Single group. See? You have how many people being employed? 100 tasters, coffee tasters. See? You have how many brands? A, B, C, D, 4 brands. So it seems like it's very similar to that what we had in the very beginning for golf ball, that example, same thing. And but under the repeated measure setting, block design setting, should be some. No, I think that's yeah, see, same like this, see, same person being see, this like a group. This is a brand A, B, C, D, and they've been even randomized too. They're not gonna give like a in an order. There's no order for that. The brand A come first, B comes second, C comes. No, they were even being that assigned to that this person, given to this person randomly. Okay. So the first time when you give to this person, they might gonna go to the 10th person. Okay, but we have this. recorded this one in such a way that seems like we have done this one first. No, sometimes this person Tracy might have done first and then like that. It doesn't matter. Randomly done. Okay, that's the randomly done, and then this randomization has been done within that. See, and they, instead of going to each one being assigned to each ball over here, same way that each brand, each uh, brand, and each testers gonna have that one. We can have like a only 100. See, rather than for each one we are assigning 100, we can just simply say that 100, only 100, that if you're going to assign 100 people to do this one for each and every brand, coffee brand, see, then you have to use a 400. That can be reduced to the 100. That's what they were doing over here. So what are you going to write over there? So now you're going to compare and contrast. So this can be belongs to what? Simply single one. You have to, you need the data. No, you need the data. So it belongs to either this way. See, single group repeated mentions like this. See. Data, one way, input. See. Y1, Y2, Y3, Y4 lines. See. For these 100 people, prop GLM model, no unique, repeated. This time you can say the brand, coffee brand, okay, rather than drug. Maybe mean, and then see contrast compared with respect to A. If you want, you can put the A, B, C, D, see, YA, YB, YC, YD. See. So there are four levels. You can, within parentheses, you can say A, B, C, D. Okay. Here you can say 1, 2, 3, 4, like that. So in this example, see, and then they have given what the rate. Rate would be your Y. See, rate gonna be on a scale of 0 to 100 to that for the perfection you get 100. You're gonna rank that one, but rate it with the scale of 0 to 100. So the YA, YB, YC, YD. Okay. Same way, YA, same way like this, YA, YB, YC, YD. Then you can get the lines, get the data, prop GLM model, say YA, YB, YC. Y means like a, Y stand for the rate. Y stand for rate. Repeated brand, brand 4. Within parentheses, you can say capital A, B, C, D. And contrast with respect to A, with respect to A. Slash summary mean if you want to. That's not how. Any question on this one? Anything? This one. Okay. That let's move on to that homework 2. That let's look at this. Consider the following data set from a question number 2. This is the first question, but this is from our homework, but it's the number 2 from textbook. Consider the following data set from a single sample repeated measure design with 3 repeated measures. See? So if you want, you can that even that for this one that you can get these values, everything, and the grand mean, everything. See, using R. See, sorry. See, you can get the row mean using this one. Row mean. You can use the grand mean. See, row means another way. Sorry. You can get the grand mean. See, this is the data. Yeah, I call that one univariate input y1, y1, y2, y3, 5, 6, 1 from right. No, sorry, this is different. 5, 6, 1, 3, 4, 2, 3, 7, 1. So for a given person, see, keep going like that. And on the other hand, when you're going to run this one with the summary mean, that would give you the, look at what they're going to give you. See, the means summary univariate. See, means 4.57, 7.12. What are those? Those are, they have done that one column wise or row wise. That's the part that you have to be careful. See, column wise, 4.6, 7.12. 4.7, 4.6, 7. I rounded to, what is the rounding rule related to this one? Let's to be like a very, if you want to give like a perfect answers at the end of the day, you can stick to the rounding rule. Okay. What is the rounding rule? What's the rounding rule related to the mean standard deviation? The rounding rule would be one more decimal than is being given. One more decimal than is being given. See? One. This here we don't have a decimals. In any case, that any of these would have like a one decimal place for by any chance they have kept to the one decimal place. Then you have to keep your averages for two decimal places. So does with standard deviation. See, I strictly stick to this one rounding rule in that way. That's why I put like that. But in sometime in textbook they're gonna keep to several roundings. But that's okay because thinking that we don't do the intermediate. Sometimes these numbers you're going to utilize in some calculation. We do not round intermediate steps. We round the final answer in any case. But in order for us to that plug in this one, you cannot get that whole this one with like a whole number of that the way that how you have set up your computer or that one to the number of decimals. So you cannot put that one when you do by hand. Better after that round that one based on the rounding rule. But you sometimes that your answer might gonna be a little bit off from that what you have in the textbook. That's okay. It's not a big deal. So this will be off because of the rounding the rules. So here what I did was that I rounded them to one more than is given in the data set, which is one decimal place, and that way that you're gonna look in the second decimal place, and if it is 5 or more than 5, you're gonna add one to the previous one like that. Okay. And these numbers, they don't show these numbers. See, they show these three numbers only that when you run that univariate. See, univariate. Yeah, they ran the univariate as, sorry, that here summary and mean, like that even with the univariate, you can get that one too. See? Same thing. See? Each one being separately given, there are all the other descriptive statistics as well. See? Standard deviation, this one, kurtosis, coefficient of variation, uncorrected sum of squares, standard error of the mean, sum of weight, and all kind of stuff. But they were done that. And then if you need the row means, see, I'm gonna try to get the row means like this way. See, this way. See, 5.3, 3.7, 5.7, 6, 4.3, 5.3. Rounded to the one decimal place. If you want that, you can go in that. You don't have to. I mean, like I did not. But I prefer that if you can use that even SAS to get all this done like that. And another one that you can use the proxy SQL. Data simply, you're going to find the mean in this direction. See, y1 through y. So let's see this one. Select mean. The same thing. And for the grand mean, I'm gonna use the SQL. I got this one mean, the mean one. 4.57, 4.57, 4.57, 4.6, 57 become 4.6. And if you use the Excel, it's a far easier, but in order to improve that skills on that SAS, you can get this done using that one if you want, but you don't have to. So then that one. Then let's get back to that question. See, you have all these standard deviation came along with that univariate row summary. See? I have I gonna go from 1 to 3 groups. G means groups 1, 2, 3. See, Ni is fixed. This one, see, sum of data down the column divided by number of rows. Called this column means. This one row mean sum of data across the row. See, sum of the data across the row across the row divided by number of columns. 1, 2, 3. That's how you got that one. Do a univariate repeated mesh analysis using calculator using the procedure employed. Sorry, here, employed in the text. Do you reject at the point overlap? See, here what we're gonna do. See, the column means this one. See, from this one, this means column. See, because of that, see, this data that the participant average responses to the 3 treatments differ, ranging from 3 to 6. 3 to 6, see? 3 to 6, 3 to 6, that range. Not significantly, but 3 to 6. Then that difference, see? That difference can be quantified, this variability, through so-called the sum of squares for blocks. Because they've been blocked. This is a given block, see? So one block, they've been blocked, okay? So participant average is 1. Quantify this variability through so-called sum of squares for blocks, sum of squared blocks, block sum of squares, SSPL, where we are blocking on the subject. The error variability, which is called SSW, within sum of squares. So sum of squared within sum of squared within is split up into 2 parts. See? This one. We used to call this error variability, that the within that one in the previous setting, like a completely randomized design, that one split into 2 parts, like this. See? From that one is stand for the sum of squares residual, sum of squared residual sum of squared, error sum of squared error, sum of squares of error, like any name you can call that one. From that one, I really need the SS residual. I don't have that one. I have SSW and SS block. See, I can calculate them. SSW within. See, I goes from every entry minus their own mean, column mean, not the row mean, column mean. See, ith group is a first group mean, second group mean, third group mean. See, 5 minus there. See, 5 minus 4.6, 3 minus 4.6, blah, blah, like I'm talking about this way. See, this way. 5 minus this one, this guy minus that, this guy minus that, and at the same time square, and then add them up. That's what we were doing over here. See? And we got this up to here, 9.7 to up to second group, 18.87, third group, 4, 32.59. Then for the block is, this has to be done over rows and column both, but you're gonna go to the Y bar J. J means this one. This means, see, this means. See, this means. Okay. Consider this mean minus the grand mean. This minus square plus this means minus this one square, like that. Okay. That's what we are doing here. So see, if there's no I because of G, G means 3. So J goes from Y bar J, which is 4 minus grand mean. Second row's mean, which is 3 minus grand mean square plus blah, blah, blah. This the sixth row mean, and it's grand mean square plus, and then you get this one. Then you're gonna take the difference between that two to give the sum of square residual. See? Sum of square residual. See? Sum of square residual. That way. I need the sum of squared block, the between. This is sum of squared between. This is sum of squared block. This is sum of squared within. Okay. So I need between. Between is given by mean 2, which means the column mean minus this grand mean. Earlier, sum of squared block means row means minus grand. Oh, sorry, I'm sorry. Here this should be square. Okay, here square. That should be square. Square. So that's for the block. This is for the between means group to group. You see that particular group's column mean minus grand mean 4.6 to 4.6. There are only 3 means. Column means I subtracted. So this one. Then I calculate the degrees of freedom for between G minus 1, G minus 1, 3 minus 1, 2. Then I go to the degrees of freedom for residuals, N minus 1, G minus 1, which is 12. Then I'm going to build up mean squared between, mean squared between. This one mean squared, not the block, mean squared between. Sum of squared between divided by degrees of freedom of between, which is 2. Sum of squared between 91.07, which is 45.54. Then mean squared residual. See? Then sum of squared residual. Sum of squared residual. We already had the sum of squared residual at a certain point. See, sorry, 10.15 divided by this mean. Then they both will be divided. See, 45 point. This one we have given 53.58. And then p-value is nothing but the probability f is greater than 53.58, which is I got this one. See? So this value and these values, do we get the same values when we're going to run that one, our homework one? This one, see? Okay, see? Sum of, okay, let's compare. Compare and contrast. Here, 45 point, see, around 45, 46, because I'm sorry that I'm looking at the wrong place. Repeated measures. Okay, 92. Sorry, I'm gonna go here. Okay, see, sum of squared between the drug. See? Sum of squared between calculated. See, this one. See, this one, and the error, the source, univariate case. See, that one, and error. This is a residual. See, 10.15, almost 10 point. See, 10 point. If you have rounded to that first decimal place, it's like that. Because as I said earlier, that is, they have considered that all the decimal places in all the means and standard deviation, all kind of stuff, especially in mean, they haven't rounded. I have rounded. You're not supposed to round because in the, but I rounded for my own calculation simplicity that you don't have to. Because if you do this one in the, if you are planning to get this one, if you get simply that only average, you can round and give the answer. But if you are planning to utilize that average in the some kind of other calculations, you never ever have a, like any kind of a rounded numbers in the middle that any intermediate steps. You have to round this guy. Okay, that's why my answers are a little bit off from what you see from this table. Okay, it doesn't matter, but roughly that pretty much the same. Okay. See residual. See this the drug. This the see the error. See 10 point something. This one 90 point something. And degrees of freedom. You saw there are degrees of freedom. Here 2 and 12 between, and then this one 12. No. And then mean squared 45, see 45, 45, 46, and 0.85. And F value 55, 53, that's okay because of the decimal rounding. See? And then the p-value is nothing but your probability that F is greater than 53.58. What that means? That means that 53.58. See, if you have a like a F distributions. This one, F naught, 53.58. And the area to the right of that one is called p-value. P-value means what is the proportion or the chance that you're going to have a numbers extreme than the 53.38. Extreme than the 53.8. This is F. F greater than 38. It's called 53.58. I'm sorry, 53.58. Okay, 58. 58. Is greater than 53.58. That p-value, you know how to get that one. See, can you remember when we were checking the p-values? See, p-value for F. See, I'm gonna put input F value, numerator degrees of freedom, denominator degrees of freedom, but they're gonna get the p-value, F p-value. They're gonna give the area to the left of that one. See, that's how I subtract. Okay, they're gonna give this area. It's gonna give this area. I don't need this area. That's why I subtracted from 1. The SAS will give you this area. So whole total area is 1. 1 minus that one will be the area to the right. I'm interested in area to the right. Okay. So that's why we have that one. Okay. 1 minus probability. You have to give the F value, which is 53.58. Numerator degrees of freedom, denominator degrees of freedom. 0.00001043. 0.001043 less than 0.00001. So that's in a similar fashion that thing. So see, that's how that if you have any numbers or anywhere around that, this is the right time to that have a look at it and straighten up or that correct wherever that you make the mistake. Sometimes when you do with the Excel, be careful that don't when you make that sum, when you drag, that you're gonna drag from that to make sure that you pick the right cell. I saw that one. If you that's the averages sometimes missing. That we should that have these numbers. Let's say for example, 5616 5 3 3 6 6 4. The other one 6 4 7 8 6 2 7 8 9. The other one 1 2 3 2 3 get the averages. Average. And then can drag this one here. You don't have to do anything. Actually, on this side to the same thing. Make sure that you're gonna start from the right place. Don't
I did
let-
not know you could drag it like that. I would copy paste.
you can drag easily. It's very-
Don't work with Excel that much as teachers.
So see, it's going to
We
feel.
need teachers to be grammatically correct.
See. Boom and all. I'm sorry, the last one we don't need. See, it's the grand mean as well. Grand mean and everything in one shot.
And then you're going to format them all to one decimal place.
Yeah, if you want, oh, you can keep as it is, as I said, that yeah, but in the program, if you're going to compare that one with the output coming from that by running our GL and repeated measures, that your answer is a little bit off from that one. That it's not a big deal. It is expected because because of the rounding. Even here they have rounded to this month. They say rounded. How far you can go? That's called the number theory. We don't do number theory. We don't know how many numbers is keep going. You see, go to infinity. See? Because of that, but that's why we sometimes try to round in the intermediate steps. But it's highly recommended not to round that one. At least to keep to like a 4, 5, 6 that decimal places for that one. That might be the reason they are keeping this one in that way that they can easily manual at the end of the day. But it doesn't matter. You can just do whatever you want. It's because we mainly that. But if it is really based on that, whatever that when you do any research or something based on your physical scenario, you have to make sure that you keep these decimals very carefully. Okay. It depends on what you are try to analyze at the end of the day. Depends on like that, but I gave like a rough idea, but to want that one, see, then we go to the multivariate one, we're gonna just build up that take the difference between those two. When you do these differences, the very moment you do the differences, your covariance becomes what? In such a way, this one, Z1 and Z2 will have the same variances. That's what we call the sphericity. That means a sphericity means like that they both have the same one, like that homoscedastic. That means like this variance of this guy as well as this one would be the same while their covariances become 0. If they were depart from that one, that's why we're going to talk about the epsilon. Epsilon is there are two types of epsilon we talk about. Which one? for the first time this epsilon being introduced to that statistical arena by Cox, we have, okay, I think I have to pull out something on it, that one. Sorry. So basically, sphericity refers to the equality of the variances of the differences. See, that's not the only way you can get this done. Why you are taking only the differences? Why you are trying to do this way only? Are there any other polynomial way can you get this done? That's one of the question we have over there. We have a question, but if you do any way, you can get this done. Sometime instead of this one, you're gonna say y1 minus y2 squared. See, polynomial. This one 2 square, 2 times this one, 5 times this one. Doesn't matter how you're gonna get this done. You're gonna do the transformation. These are transformation. You transform. It doesn't matter. Eventually, you're gonna get into the same answer. That's what we call the invariance property of this repeated measures test. Invariance property. We're gonna have the same answer, but this one here, when you do the differences, see, basically sphericity refers to the equality. They have to be equal variances of the differences between the levels of the repeated measure factors. There are p repeated measures. Okay, we transform to p minus 1 now variables. Okay, p or p minus. Okay, let's say, look at here. See, right after this transformation, if you have a, let's say that, I'm sorry, this is not the right letter. So sorry, this one. There are p variable. Okay, that's okay. P variables. That's what I meant over here. Okay, if there are p variables in the beginning, you can get the p minus 1 new variables. See, if you have a 3 variables, you can get the 2 variables, one less than that what you had. Okay, by if you take the differences. See, new variable, there are other choices for this p minus 1 variable than the adjacent differences used in the previous drug example. That means this is related to that our note that, see, this in the beginning we had that drug example. Okay, so see, some multivariate which will give the same multivariate test statistic. This is what we call, very important, this is the what we call, oh sorry, see, that's the invariance property. Invariance, see, it's not going to change. Invariance. Invariance property. Okay. This is the place that where they mention about that what's going to happen, that if you're going to, instead of using this transformation, if you go to different polynomial transformation, what would going to happen? Nothing's going to happen. Your test results would be the same at the end of the day.
So basically, it's similar to an algebraic equation. If you do the same thing to both sides of the equation, it doesn't change the outcome.
Doesn't change at all. Yeah, this is that's an invariance property heavily utilized even in the estimators. Estimators too. See, when we estimate, that invariance property heavily utilized, it's not going to change. See? It doesn't matter. Anyway, you can set it up. As I said over here, not that differences between two adjacent groups. You can get the difference and the square that one. You can get the cube of that one. And cube plus something, any polynomial. You can think about not only y1 minus y2. Not y, I'm just take the y1 and y minus 2 and think about other polynomial. You can take the square, see? And you can get the cube, see? Still okay. And you can put another number here and plus add another constant to here. So many things you can get, or divide by this one certain number. Let's say 4 or something. Anything. Square root, take the square root, anything. but still you're going to end up with the same answer at the end of the day. But you, whatever you did for these two, and you do the same thing for y2 minus y3, y3 minus y4, so on like that. See, adjacent one. See, new variate selected are, see, orthogonal, uncorrelated. That's very true. There's no correlation. See, new one. In the beginning, you have all the p variables. But how many variables you have in the beginning? They were correlated. Can you remember? They are correlated. Now no more, uncorrelated. It's called orthogonal. And now scale in such a way that the sum of squares of this, their coefficient for each variate is 1. If you get the coefficient and square that one, see, for each variate, then that will sum to 1. Then you're going to call the orthonormal, see, orthonormal, see. Then we have called orthogonal. This one, sorry. See this one, this one. See, is this transformation? See, this is how that one. You don't have to worry about that. Think about this one. See, no more correlation. See, and on the other hand, their center or the main diagonal, this is the main diagonal of this matrix, should carry the same variances called the homoscedasticity. Homoscedasticity or that homogeneity or that sphericity, the different names we can utilize. See, but see, if it is departure from that, see, saying that the off diagonal elements are 0 means that the covariance for all transform variables are 0, which implies that the correlations are 0. So there's no correlation among those variables anymore. You had in the beginning you had 4 variables, now you have 3 variables like that. You had a p variable, now you have p minus 1 variable. That's the same thing we are dealing over here. You had 3 variables, now we have a 2 variables, z1 and t2. z1 means y1 minus y2. For our convenience, we're going to go to this difference between 2 adjacent groups. Okay. Right there. The extent to which that covariance matrix deviate from the sphericity means like this one. If your covariance matrix is deviate from that one, it's reflected from this epsilon. See? That's how the epsilon comes into the picture. It's sometimes they say epsilon is utilized in that thing for infinitesimally small amount back in that calculus, but here, to denote this one, epsilon, see? See that one. See, there are 2 types. See, greenhouse, geyser, epsilon. Actually, the box, okay? Box proposed the measure of the sphericity to be this one. See, it's coming from the population covariance of the original data. See, and it goes from see this many groups. See this many groups. See this one. Look at there. Cij means any. See, this is population covariance matrix. There, see, if you go to that center one, sorry, the diagonal one is denoted by ZII. This is any of them. See? Then box approach works for the population covariance matrix population. But unfortunately, in general, this matrix is not known. We don't know this one. You have to estimate. How do you estimate? In order to estimate epsilon, see, we need to transform the sample covariance matrix into an estimate of the population covariance matrix. But when you have, in order to do this one, when you have a sample, that the covariance matrix in your hand. It's not enough. It's not enough to get the estimate. Estimate of the population covariance is not sample covariance. That's what I want to emphasize over here. S is not an estimate of sigma. The estimation, all the entries are done through this way. The given that your estimate matrix, it's a new covariance matrix, therefore that the estimate of this one, see, this one psi, is psi or what, that later, yeah, let's call this one psi. So this SC from that sample one, go to the one of the entries minus its mean of that related to that particular row, mean of that particular column plus the grand mean. See, this way, this the way. That one is they call the double centering. And then for that particular double centered covariance, then this one they built up a double variance covariance. Then we put this formula. This formula. It's a one way of getting this one. In our homework, we don't have this formula. We have alternative. See, an alternative way to calculate GG epsilon is using GG stand for the greenhouse and Geyser. Using the you can use the lambda too, but lambda is not coming from the original matrix, double centered covariance matrix from this guy. And there's another way to look at this. This the alternative formula is the one that being given in the textbook for the exercise. This is the formula you see. In question number 5, this formula. Okay. You go to the original one, see, alternate formula. S bar and the all kind of stuff. Okay. Yeah, S is a sample covariance matrix. The mean of the all element image. The mean of all elements in the diagonal is SASA. Sometimes you can use this one SSI and bar. Okay, and bar. And the average. Okay. And in addition to that one, that Huyn and Feld, they develop this one most of the time underestimate this epsilon, underestimate this underestimate. It's not a sometimes conservative, very conservative. Underestimate. This one overestimate. This guy. Oh, sorry. It's counterpart. Huyn and Feld epsilon. Whatever he did, he got that GG and did some kind of a modification. Did some time modification to get this one. Okay, these two will be okay display on your printout all the time when you when you run. Let's say that let's go to homework 1 and run. See, they will be displayed. See, so here, see, greenhouse guys epsilon and then Huyn and then Feld epsilon. See, they will be displayed. Okay, they will be displayed all the time. And this is how you get that one. This one, this is more liberal. That's overestimate. This one underestimate. This one GG. This one overestimates. And sometimes some people, what they're gonna do, they're gonna get this one and then take their average. Take the average of those two. And on the other hand, sphericity between 1 and 1 over G minus 1. See, this condition is met, epsilon is 1. The worst possible one, 1 over G minus 1, epsilon. See, if it is this homoscedasticity, that means like all the groups gonna have the same variance. That condition is met, then epsilon is 1. They will fall in between these two extremes. See, lower bound and this one, upper bound. It's a lower bound, this upper bound. Between that one, every epsilon gonna fall. That will tell you how far, how your covariance matrix being departed from that sphericity. That means like that having this kind of a, instead of having this kind of a covariance, sometimes it's not going to be the case all the time. We are expecting this one. This is the ideal case. This is what I'm expecting. It's not going to happen. How far your covariance matrix? I'm talking about the transform covariance matrix. Right after transform, how far these entries being away from this what you expect, not having the same variance is, see, even by this much. Okay, and sometimes what we're gonna do, we get this one and then do the changes for the degrees of freedom. Degrees of freedom will be rectified by these epsilons. Okay, to that one too. But anyhow, that if you go back to this one, okay, multivariate one. I'm gonna come back to that one. Then I got the means, I got their variances. Then I put both together, okay, and transform. This means bar, this means vector, this means transform. And I get this one. How do you get this one? See? How do you get this one? You have that when you have this guy. How do you get this one? Hmm. So, okay, see, you can get the covariance. See? Covariance you can get, see, up to here, see. Covariance matrix. Z1, Z2, 1.6. There's a covariance of this one, see. I call that one, see, negative 1.5. I'm talking about that new data entry, okay. I'm gonna call that one data multivariate, input Z1 and Z2, lines based on what I have here. Here, I'm talking about this one, see. These entries, okay. These are the minor. For this one, they create what? This guy, this one, 1.6, negative 1.6 on the right. See, covariance you can get by giving, see, you ask him go to the correlation procedure and then give the covariance. See, 1.6, negative 1.6, negative 1.6, 2.5. 2 by 2, because there are two variables now. Now you're gonna get the inverse. How do you get the inverse of that? You get the in. Okay. So I'm gonna get the inverse. See, I'm gonna get this one S. I put over here 1.6, negative 1.6. Next this one is the D, because I'm trying to get that F2 at the end of the day. That's why I'm trying to do everything at the same time. So the D would be the difference, 2.6 and 5.1 D. It should be D, not the D. I can call that a D bar. I think that's D bar, D bar, D bar. D bar means the mean of the difference. Mean of the difference. So I'm using that interactive matrix language, IML, okay? So I'm gonna this observe. Okay. D bar, D bar, yeah, here I have a D bar transform. It's not being set. Let me see what happens. I'm gonna go with what I had earlier. Okay, let me see. Here, 2.6. Yeah, 78 that T squared. Okay. And if you want, you can print even this guy too. S in. That's the inverse one. This is the T squared. Okay. But anyhow, that see, I call that D means like my D bar. Okay. The mean. Okay. Then I put the by. I'm talking about this one. See, I'm talking about this vector. Okay. This one. This is the one that I put over there. This is the one that I put S. Okay. I call this one S. I call this one D. Okay, in my program. Okay. S and D. Then I get the transform, see? Transform. See? This one, see? If you go ahead and then it's right below that in your keyboard, right below you have a tilde, you have this one, see? This one. Then I S in getting from the, I'm gonna call that S in, and the t square is nothing but, t square is nothing but, see? Okay, t square means 7 times mean the transform. So when you put over there, if you have a given that your vector like this, don't call that one transform. This is my transform. Your transform would be column, okay? That's why it go the other way around. I'm gonna call this one just simply D. Then its transform would be this, okay? That's what I'm trying to say in program for my command. This is okay. Okay, this is your transform, this is your D, this is your S in, this is your N. I multiply all these and 78, 1.8. See, I get the 7, I get the D. D means like this one, the row vector for my averages and the inverse of the covariance matrix and the column one. And then I'm going to print both. See, if you want, see, you don't need that one, this one, because it's 1.7, 1.7, 1.11. Is that the same thing that I put over here? It's 1.7, 1.11. That's how you got 78. And you do the adjustment for this one, 78 to now you're going to convert this t squared into f by this one, the original one. Okay, n stand for how many individuals, 3, how many groups in original one, not the transform one. Be careful. In the transform one, you have a 2 groups. Okay, in the original one, you have a 3 groups. Go to the original one. See, plus 1 and divided by 7 minus 1, 3 minus 1 times this. And the degrees of freedom for numerator is nothing but g minus 1. Degrees of freedom for denominator is nothing but n minus g plus 1, which is for 2 and 5. Okay, now we can see we go 32.5. Let's say where is my 32.5 in our printout? Okay, I'm gonna go back to this one. Multivariate already included except for the CRD, univariate and multivariate. Where is my 32? 32. I don't see anywhere 32. This is a univariate case. This is the multivariate case. But multivariate case, I don't see 32. Yes, I see. See, under the Wilks lambda, Pillai, Hartley and Lawley trace, Roy's greatest root, they all pretty much more or less produce the same result. See, and the degrees of freedom are numerator and degrees of freedom for denominator being 2 and 5. See, look at this. Around 32, okay, because it's off for this, you know, they are off from my answer, or my answer is off from the answer because that I have rounded my numbers, especially that averages. Okay, so these are same as whatever you're gonna get it from this procedure. See, the multivariate repeated measure f value, which is f naught 32, agrees with that of Wilks lambda, Pillai's trace, Hartley and Lawley trace, and Roy's greatest root, which is f naught 32 within rounding error. So you can use any of these. When you're using the Wilks lambda is same as you are using this, the results coming from this procedure by looking at, if you know f naught, you can compare contrast with critical value, and then you can easily get it done with the result. You can see whether your test is significant. What is your test? Where is your test? Where's the test? What is the test? Did we write the test? But we are trying to, what's the test? Test would be same test. New one. Can I remember we talked about that one the other day? Okay, related to this one, I can write here again. I did that one the other day. H naught, okay. equals population average of mu1 and same as population mu, okay, mu2 equals mu3 versus its counterpart, which is at least two of them not going to be the same. We know that one. Or equivalently, you can write this one, same thing. See? Same thing you can write H naught. See? Oh. Mu1 minus mu1 equals mu2. And the other one, H naught, mu1, mu2 equals mu3. Okay. And equivalently, you can again write H naught. I'm still writing the H naught. Okay. H naught mu1 minus mu2 equals 0. And H naught, the other H naught, mu1, mu2 minus mu3 equals 0. And we are tackling these two at the same time using the multivariate approach. That's why I'm going to do this way. Because I need their difference, average of the difference. See, I need the average of this. This is nothing but Z1 bar, same as Y1 minus Y2 bar. See, like that. See, this one. This is nothing but C1, C2 bar. C2 bar means Y3, Y2 minus Y3. Like that. These are the variance. Whose variance? How do you write the variance? Va of Z1 O va of Y1 minus Y2. And so does the other one. You can write like that. Okay. So see, so those results coming from this one are same as the other one. Now, on the other hand, that results that the Pillai and then Hotlin Lowley's Wills Lambda, where are they coming from? They come from through this procedure. I roughly showed you because these are very heavy. You don't have to worry about that one. See, this has been settled. This is related to the next next week. We're gonna have a multivariate analysis. It's related to that one as well. But here that, see, like if you have some example like that, instead of one variable, thinking about one variable for given group, see, let's say you have two groups. You have only one variable, one entry. Here, two entries or three entries, 5 entries. You have any number of variables within that one can be tackled at the same time. See, this is a very generalized format. So see, this is the group. This is a group being given by I. In which group you're gonna be in that one, which population, and the J gonna be that which individual. See, this group, or this group. This is the individual. See, it's the individual. Second individual, third individual, like that. See, in one case you have 3 individuals. In another case you have 2 individuals. And P stands for how many variables you tackle at the same time. How many variables within that? See? 2 variables. 2 variables. 2 variables. 2 variables. 2 variables within that. You have a 2 variables. This is equivalent to the 2 variables, 2 variables, 2 variables. How many? 1, 2, 3 people. Okay. Let's get back to Z1 and Z2 here. See? 2 variables, 2 variables, 2 variables. How many groups? You can consider this one as like a one group. One group, 2 variables. one group, two variable. How many n? 1, 2, 3, 4, 5, 6, 7. Same thing being flipped over here. See, that's the same thing being flipped over here. I'm going to consider only this part. This is like my Z1. See, this is like my Z2. See, think about that. You can consider that one. That means how many groups you have? Just a one group. See? Instead of three groups, you have one group. And then how many individuals? 1, 2, 3. In our case, we have a 7. 1, 2, 3, 4, 5, 6, 7. And see, like that. See? P is 2. See? Equals 2. Like that. See? This is they tackle this one. The univariate case, same thing. Okay. In a univariate case, you have a square. See, this is how you're gonna do univariate case. You have yij minus their own mean being squared. Now in matrices, square will be given by this time it's transformed like that. Keep going like that. Then you have a b, you have a degrees of freedom. Then from this one you got the Wilks lambda. See, this is how they got the Wilks lambda. And these are the condition under that, these different conditions. See? When we have a g equals 1, do we have anything fitting into this one? Or when p equals 1 and g equals 1, see, so many variations, many variations. And then the other variation, instead of f, they're gonna go to the p chi-square, okay? They can use that one too. Or Hotlin law means like those variables trace. We talk about that one the other day. You're not going to calculate anything. And even the lambda, Wilks lambda, you can express in these ways too, with the aid of the eigenvalues. Another formula for the replacement substitute formula for any of these. And Wilks lambda again can be get it done in this way. See, you're going to get A, you're going to get B based on that your condition. You get C, and you get degrees of freedom. You get this guy and Hotlin, see, right there. See, this one. See, sometimes you can use this one to get the we can by hand. You calculate and see the Wilks lambda that you got it from there is as the same as this one. See? You can check that one. Okay, Wilks lambda when changed. Okay, with the aid of the Wilks lambda, whatever the coming from that one, the p value, see, sorry, the f value, I'm sorry, talking about the f value is same as, see, that would come in from when we calculate our through this procedure. See, this coming through this t squared procedure is same as Wilks lambda. See, see all these procedures, Wilks lambda, Pillai, Hotlin, rho is greater. When you're gonna make a conclusion, you can just get this f value or the one of this p value and then do the conclusion. That's the same as that you have done like this way. That's what I'm telling you. Do that by hand. You did that one in homework 1. See, by hand. See, you did this one. Sorry, this one. See, you get the answer. But on that printout, how could you gonna see that answer? But only from that that table. Okay, that table you don't have like this way. You have like a Pillai, see, Pillai's lambda and Pillai's trace and Hotlin trace and the rho is greatest root and then blah blah like that. Okay? See? Look at that in the see. That again that we're gonna talk about the epsilon, that the extent to which the covariance matrix deviates from the sphericity is reflected in parameter. Is the sphericity matrix. So this one, if sphericity violated, gonna be 1 over this one to adjust to the possible the is this bias. I'm sorry, bias. I cannot read even what I wrote. Bias here. A lower bound estimate of sigma can be used, although this makes this test very conservative. Okay, lower bound you can use. This approach alters the degrees of freedom from here to here. You had the degrees of freedom like that to 1 to this one. See, 1 to this one, because you're gonna think your g in my g minus 1 is 1. See, G minus 1 is 1 to make this one 1. If you want to make this one 1, the only thing you can do, you can substitute G minus 1 to 1. Then that 1 comes here, and then this become 1. This become 1 times. See, you change that one. But the modified degrees of freedom increase the critical value to which the F test is compared to determine the statistical significance. It's going to increase that one. So that means that you are pushing to that to get rejected and to make the test significant. That's not good way of doing that. However, this lower bound estimate of sigma provides too much an adjustment, making an adjustment for the worst. See, it's going to be the worst possible case. See? So because of that reason, we're not going to go to that lower bound. See, they say go to the lower bound one. See, G minor, in order to get the, think about the tackling this one in the lower bound. If you do the adjustment to make this one, the sphericity is met, you have to make this one 1. In order to make this one, you have to substitute G minus 1 should be 1. If it is 1, then your degrees of freedom going to change to 1 to this one. That's not good because that's this lower bound estimate of epsilon provide too much adjustment. See, go to this one. That's why they were saying because of this procedure is too conservative, we don't recommend it. The more measurable approach is to estimate that one. 1 epsilon is estimated, degrees of freedom going to alter from this to that, see, and multiply by epsilon hat and this one. And one of the epsilon hat would be, as I said earlier, see, greenhouse epsilon tends to that underestimate. Underestimate means conservative epsilon, especially when it goes to 1, while Wien and Feld tends to overestimate, which is rigorous. One possibility then is to use the average of estimate, see, average of both of them. Generally, the recommendation is to use the EGG, especially if epsilon had become less than 0.75. If it's more than 0.75, you're going to use this one, Wien and Feld one. See, that's the cutoff value. Okay, then so then for this example, sorry, I did that one. For that particular example, for the homework, that one, see 1.6, this is 1.6, 1.6.7. Can you remember? That's the covariance matrix, no? We got that one covariance matrix. And have a look at it one more time. See 1.6, 1.5. What's covariance? 1.6, yeah, that's the one. 1.6. 1.6, 1.6.6 covariance matrix, and I tried to calculate that one by hand. Epsilon. In order to do that one, I'm thinking I'm using this formula. Okay. That's the same question you have in question number 5, but I'm trying to do the same thing, even though that this being displayed on that. This will be displayed very clearly on that one. I want to make sure that whatever I see, I can get this done manually as well. That's what I'm trying to do over here. They display here, okay? They displayed here, see? Greenhouse, the guys epsilon and the Wien Feld epsilon. They both. This is very powerful, this second one. Second one is very powerful. But anyhow, that so anyhow, that sorry, we see the result. Yeah, these two. See, I want to see whether I can get the 0.7844. See? And then from 1.013, once you know this one, okay, that's what I'm trying to do over here. I got the covariance matrix, original one. Then I got their reading, see, every reading and I squared, see, 1.6 square, 1.6 square, blah, blah, all the way up to this 9, all the 9 entries I squared. That's what this whole thing means. Sij squared over I over j. Then mean of all entries in the covariance matrix. This is the square of the ijth entry of this one. It's a mean of all entries. I added all the entries together and then divided by 9, 1.3. Then I get the mean of all entries in the row of this one, row I think. This mean, row means 1.6, 1.6, 0.7 divided by 3. 1.6, 3.1, 0.7 divided by 3. 0.7, 0.7 divided by 3. Then I got that one. Then what I did was I got this average, I squared 1.3, 1.8, 0.7 and add together. Then I'm looking for the mean of entries on the main diagonal. See? 1.6, 3.1, 0.7. 1.6, 3.1, 0.7, which is 1 point. Then I plug in into this formula. You have a g squared. You have a I bar is 1 minus s bar grand mean of these entries divided by g minus 1 times all the entries square and then sum them up. All the entries square and then sum them up. Okay, minus 2 times g and the bars square, row bars, 2.52 g squared and grand mean. I put that one, but it seems like it didn't come to that one. I think sometime maybe some mistake who rounding rule like that. I want to double check this one. Okay, I want to double check this one. It is not what we see on this one because there should be some mistake somewhere because look at here answer 0.78 approximately 0.78. My answer is point. I want to double check. What? See? Oh. Then what I did was I assuming that okay. Then sorry. Then when you adjusted that you have to multiply by no. This is not right. It's not right. It's 0.46. Even not the 0.4 is 7. Then what I did was assuming that this one, then I came to the other one, assuming that the right one, okay, not my answer, the answer that I had for on that SAS printout that I had for this GG, guys, and this epsilon, I utilize that epsilon and calculate the other one using the other formula. So for the mean and field, see, they say whatever you got from this guy should be rectified like this. So what I did, the 7 n e3 0.7844, okay, minus 2, then 1.0135. That's right. It is very consistent with. So there's some mistake, something wrong somewhere in my calculation. I had to double check here, but they didn't ask us to do that one, but it's something that I did for me to make sure that we're using the right formulas. See? When they have given that formula in question number 5, see, like that. See? Then they see in the number 5 the same way that that's formula. This formula is the GG formula. That's the same thing. But that one, when you get they have no decimals. That's easy. See? GG1, 4 square, 3 square, 2 square, 3 square, 5 square, 3 square, 2 square, 2 square. Since I finished this one, I skip that 3 and jump at this one, but we're gonna go through that one. If time not gonna permits me to finish everything, what I'm gonna do, I'm gonna make another video, not this one, another video, and then I'm gonna upload, okay, with the other answer and then all the explanation, okay. So it's pretty much that I had to jump into the other class, but so for this one, number 5, see, S bar I got by adding all the numbers and divide by 9. Got this one. And then row means 4, 3, 2, 4 plus 3 plus 1, 3, 5. this one, 2 plus 2 plus this one, then they are squares, and then add them up, and diagonal, the main diagonal, see, main diagonal number, see, 456 divided by 3 average, and plugging into this formula, it's 0.82. And on the other hand, that because that is like that amount of time that I'm gonna, as I said, I'm gonna make another video and then upload it. But there's another question, talk about the multiple comparison to get a rough idea which post hoc, after that that you have done with your major that test, you want to make sure that which variable gonna be the best group, best brand, best drug at the end of the day. You cannot get it done using the ANOVA. You need to do the multiple comparison. Okay, it goes like this way. Do you have a set number of planned comparisons? If you have a plan some comparisons, yes, you use the Bonferroni. If not, then you have to question and ask, are you making a pairwise comparison or not? If you use the pairwise in comparison, if you're not using the pairwise comparison, not two only, like a pairwise means like a mu1 and mu2, see, mu2, okay? You're supposed to, in ANOVA, you are comparing mu1 equals mu2 equals mu3 equals let's say mu2 equals mu3, see? In our example, okay, mu3, okay? But pairwise means two at a time, see? Two at a time, you have a three choose one, which is 3. You have 3 combination. That's true. Mu1, mu2, mu1, mu3, mu2, mu3. See? So if you do pairwise comparison, if you're not doing that and go to Shefe, that means Shefe is doing some kind of a adjustment like this. Like you're gonna say that 3 times mu1. How 3 times mu1 is equal to 2 times mu2, something like that. That 3 mu1 minus 2 mu2 equals 0. See? Then this, you can select this order that coefficient in a such a way their summation should be equal to 1. There are conditions you might have done in previous class into that ANOVA, I think. Yeah. But then you're gonna use the Shefe. Shefe, if you are not doing that, if you're doing that, then you do the same size as among the groups. Yes, you do the Tukey. If not, you go to Tukey and Kramer. So this is the one they're gonna ask us, the Bonferroni, the predetermined one. So we can talk about that a little bit, and then I can see in the Bonferroni pairwise comparison, the Bonferroni procedure is easy to use. And there are G treatments, D groups, okay? A brand, B brand, C brand, like that. Here in our case, we have 3 groups. Then there will be GC2, G combination 2, see? 2 will be compared, see? Or this notation, or this notation, or simply this is multiplication. This is how we simplify it. You get this number, you're gonna write its factorial. And you're gonna write the factorial with the same number of elements on the top. You don't go to the full factorial here. You stop here because you have 2 elements already written here. You write the true written 2 only numbers will be written on the top. See, you have a G minus 1, see, G minus 1 as an example. When there are 3 treatments, there are G means 3, 3 minus 1 divided by 2, 3, they add comparison. If you wish to overall alpha, your alpha to be 0.05, then in order to get all the pairwise comparison come together, at the end of the day, when you add that one, in order to get that one, you're going to do some kind of an adjustment for your level of significance. What is the adjustment? Alpha divided by this one, okay? Oh, no, I'm sorry, 2. See, alpha divided by, for each pairwise will carry this alpha, not the overall alpha. In order to get the overall alpha, you split that alpha into several parts, and then put together you get alpha. See, how do you split? Alpha divided by G times G minus 1, which is, in our case, it is nothing but G times G minus over divided by 2 is our factor combination, which is 3. See, your new alpha will be this one. See, so you do the testing. comparison and the testing with respect to this level of significance. Okay. I'm gonna stop over here. Other questions and everything, I'm gonna make in another video in addition to this one, okay? And upload this weekend, maybe tomorrow, maybe Saturday, okay? Before Sunday, before Sunday for sure, okay? So do you guys have any question, anything? If not, I'm gonna let you go and you guys have a good night. Enjoy your weekend. Have a nice weekend. See you guys on next week, okay? You
Hey,
will
good
have
night, Samia.
good night and then stay safe and be well. Take care, okay?
Let's post this video, Professor, because I'm gonna have to watch the end of this again.
Okay, I'm gonna post it. Don't worry. If I'm not gonna go to sleep, if I'm not,
Don't let your computer crash again, okay?
no. I'm gonna post it right away when it's it's processed. It's gonna process.
Okay.
Okay, I'm gonna post
Okay.
it. Okay, have a good night and take care. Bye. Take care. Good night.
Yeah, Samantha. Thank you.
Thank you. Thank you. Thank you. Thank you. Take care.